When we think of insulation, that's what we're usually thinking of, the glass wall that we're whacking our walls and our roofs. We've reduced conduction because we've taken a bunch of glass and spun it and separated those fibres. But although there's going to be fibres running from the warm to cold side, they're very thin.
And this is the same as Rockwool too, or a polyester glass. It's all the same principle.
The mechanism is identical.
Yeah.
All you're trying to do is take a cheapest chips material that you can spin into a wool. Our woolen jumpers, our t-shirts, everything operates in the same way. All of these fibrous materials is we're just trying to create as many small air gaps as we can for as little dollars as we can.
So why haven't they then been able to pump like an argon gas into the insulation and to improve the value of the insulation?
Well, in theory, I guess you could do something if you then covered it. So needs to be closed.
Yeah.
We know what building sites are like. Someone's going to punch a hole in it. I mean, this is the, if we have a concern with, at the extreme end, we now have these vacuum insular spans, which are, and extraordinarily good thermal performance. But on a building site, you just need to be careful because all you need to do is punch a screwdriver through that and it's going from super performance to no performance. So let's talk about space.
Yeah, okay.
Right? This is what really gets the BMI bonnet going, is every product manufacturer says invented by NASA. All of them say this. And they're usually flogging a foil-faced material, and they're talking about inactivity. And they are absolutely sort of right when the space industry uses foils all the time. So you think of your classic satellite or spacecraft. You know how it's got that, looks like wrapped in tin foil. What's going on there? That is to reflect the radiant energy from the sun. Because if you're in space, you've got the sun's rays hitting your spacecraft. How do you cool it? Now, you can't cool it by conduction because you've got space, a vacuum around you. You've got nothing to conduct to. You can't convect the heat away because you've got no air. So you've only got one way in which you can cool your spacecraft, radiation. And that's why you have the tin-faced, whatever materials they use.
Just on the NASA stuff, and I think it's 3M have invented this really thin kind of wrap which has an R value of like R4 or something. Have you heard of this stuff? Like, it's really thin. How? I don't know how. I don't know how.
It's like the thermal brake strips for steel frames. I've got thermal brake strips.
I mean, we might have to find some kind of show note to put it.
It's all about suited. But it's probably a good point to touch on because do you want to talk about the lambda value and then how then the thickness of the insulation and transcribes into performance?
So the lambda is the thermal conductivity. It's a material property. That's a point thing we understand here, that it's a fundamental characteristic of the material.
That's from you're seeing this piece of hair. Everything that we see might has some form of lambda value.
A lambda, yeah. And so for to give some rough numbers, your standard glass wall insulation bat is about 0.04 watts per meter Kelvin. A low value. Lower values are better, less conduction. Then you go through just things like pine timber, softwood timbers, they're about 0.13. Hardwoods are a bit denser and therefore have more conductivity, they're about 0.18. Aluminium is several thousand, and steel is about 50. You think of it as a ratio. 0.04 is my best case, my glass wool bat. If I just build a wall straight out of timber, say CLT, then it's about 0.13. So all that tells me straight off the bat is if I want to get the same R value or thermal resistance out of a wall, and I make, let's say it's 100 mil of glass wool, then it's got a certain R value. If to get the same out of a CLT wall, it's going to be 3 times as thick because the lambda, the thermal conductivity, is 3 times higher than that of the glass wool. And then how I'm going to build that wall out of solid steel, 50 divided by 0.04 is some huge number we need a calculator for. But you're going to have to build that wall 10 meters thick to get the same thermal resistance at 100 gram plus.
Yeah, right. So there's a really good argument there for not building your home out of steel.
Hold on. You can build out of steel, and I'm one of the biggest people who have said steel sucks for framing. But if you were then to insulate externally, could it be possible?
Absolutely, yeah. As long as you've got a continuous layer of it you're essentially separating your structural layer, the steel framing, from your insulation layer.
Which is typically not done.
Which is typically not done in Australian practice, but is done internationally.
Yeah.
And then it gets in principle, you go, well, that's easy enough, I'll do that. But then you've got to remember, you've got to put the windows in the insulation plane, not in the structural plane.
Yeah.
And what are you going to do at your slab junctions? And you've got, the details might come back to bite you.
Yeah. Yeah. And the aesthetics and all that kind of stuff, lock and finish. So you touched on wind washing before because, and I know everyone uses an analogy of the jumper and the Gore-Tex jacket and all that kind of stuff. But, and this is relevant again to a project that you and I are also working on together. And I guess the point I'm trying to get at with this question is that not all insulation is made equal because some perform differently than others, even though they may have the same R value. They depend. Yeah, exactly.
So when you look at the data sheet for a glass wool product, you'll get different level of thermal conductivities reported. I use 0.04 as an example, but it will vary from anything down to about 0.033 up to about 0.05. And so at the lower end, the better, so lower air values being better, that 0.033 range it tends to be a higher density glass wool. So what they're doing there is they're spinning the glass wool and they try to create, in the same thickness, more air gaps. If I can have, to pick a number, 100 air gaps in that 90 mil thick bat versus 50, then all else being equal, I would expect that to have better.
So more smaller air gaps are better than less bigger ones.
Correct.
Okay.
Correct.
And density is also with the sound, though. I think this is the other thing that so many people that are like, we put R4 between our subfloor and our first story. But it's like, well, we shouldn't be looking at insulation there. It's useful, but for sound, not for...
And so gives them acoustic damping as well, absolutely. But the difference in those glass wool products, and this is the same between a wall glass wool bat and a ceiling glass wool bat. If you compare your data sheets, is the wall glass wool bat tends to be denser because they're trying to stop the slumping in the norm. And so the thermal conductivity, flanders, tend to be lower. So they'll tend to be anywhere between 0.033 and 0.04, sort of rule of thumb. Whereas when you look at your glass wool ceiling bats, they're much lighter and fluffier. They're lower density. So your wall bats are sort of usually in the 20 to 28 kilogram per cubic meter density range, whereas your ceiling bats are closer to half that, about 10 kilograms per cubic meter. And therefore the thermal conductivity is higher. They've got more larger air gaps.
So is that in a ceiling? So if I was to say, hypothetically, if I put 2 R4 HD bats, that would be better than 1 R8 bat.
No.
It's the same thing.
The same high value, but you've got better thermal conductivity because of material property. You stack those 2 R4 bats. So HD high density is the usual background that the manufacturers use. Those R4 bats are usually 140 mil deep.
Yeah.
So you stack 2 of those, you get 280 mil length. Your R8 bat is north of 300 mil.
So it's just getting into a smaller amount instead.
Yeah, it's
okay.
So here's a question. You talked about slumping before. So our R6, R4, whatever they are, over time, potentially, the R value of that wall assembly could change. If we're talking about in a roof space, that 300 tall bit of insulation might...
Don't they just sag that? I thought they only go that way, not like lengthways, like that. It doesn't do that.
Well, in a ceiling, you will get some slumping, but they have a binder to try and maintain them off over the decades. Now, if you go and wax stuff on top of them, or you've got a layer of 400 dead rats or something, some kind of finicky, it is going to slump over time, and you will therefore produce the thermal performance of that bat. So what was nominally R6 being installed, it is now performing like R4.
Right. But that's why the rubbing probably is even better with external membranes and a nice and airtight. And with it side, you're not getting things in there, you're not getting wind, it sits there and it's done.
Which is back at our Gore-Tex woolen jumper analogy. But the slumping problem is more problematic in a wall because it's of course got gravity, so you've got a 1200 high bat.
Yeah.
And so you got the self-supporting weight of that bat. And if you go a super lightweight, cheapo, fluffy bat, over time it starts sagging at the top. And so under your noggin, when you install it, you put the bat hard up against the facing nog. Now it's dropped down and you've got a 50 mil gap.
And as Jess says, so when she's probably selling this from somebody else, cold spots equal bubble spots. And if you've got that slumping at the top of the wall assembly, you've got a cold spot there, which could potentially lead to molded condensation.
And from a thermal point of view, this is not a linear problem. Yes, you've got 1% non-coverage in that wall, which is eminently doable. Even a relative regeologic insulation still means you're still going to have some tiny little gaps there. Yeah. Then you're reducing your thermal performance by the order of 10%.
Yeah.
If you have 5% non-coverage or 10%, which is far more common in your standard build where they
cut out around your air cons, your power points, or anything, flow pipes.
Then it's not, you're not having a 10% reduction in thermal performance. It's much, much greater than that. It could be 50% or more. So what you told your client, well, we're going to have R25 in the walls, is now performing like R1.2.
So I kind of want to go back and like broaden this out as a very basic concept with insulation. We insulate not just your walls, but I think most people think you do walls and ceilings. Like they're the most common areas, but floors, and that means slabs and subfloors both are insulated.
Well, and this is where it really does depend on what your climate is. So if you're, say, Perth, Sydney or North, that ground coupling, so you put a slab on straight on ground without any insulation can actually be beneficial because you can use the ground as a heat sink.
Okay.
So because the ground temperature, especially say in Darwin or somewhere, is going to be as cool as or colder than the ambient temperature for much of the year.
And it's stable too.
And it's
so a subfloor then in, say, Darwin, just still insulated?
Probably because if you're air conditioning your house, yeah. Because, and this is the other thing with insulation, isn't it? Insulation is great for me in winter, but it's costing me in summer. It's like, well...
I mean, I'd also argue you have to be, without being a risk of circling back to a joke that we said before, it probably depends on how open that subfloor is as well. Because if it's on stilt and it's completely open, you've got lots of wind washing, then, yeah, you probably want to insulate to cover it. But if the air in there is relatively still, you're probably not going to have...
Maybe, but you've also got an exceptionally humid climate.
Well, this is all very true.
So you wouldn't just so now you wouldn't just have your barrier, your joist, your chipboard, because the humidity would just soak into that chipboard. Wouldn't it be
we get mold on the bottom?
Yeah, but a lot of that will depend on whether you're air conditioning space. So think of your classic tropical home that's got the louvered windows, very open, and so outdoor remote. They operated pretty well in an extremely difficult climate because they weren't air conditioned. It's once we started air conditioning those homes, you're driving the interior temperature below the exterior dew point. And so as that moist, super hot, 9% relative humidity air gets in through that wall or up through your subfloor, gets inside, got your AC on at 25 degrees, it drops below dew point, got this massive amount of moisture in that air, or it's getting absorbed into your structural floor sheet, and you're in trouble.
So this is probably, when you say moisture and stuff, talking about insulation, then all insulations are different when it comes to touching moisture and dealing with moisture as well. And just putting a certain insulation in a certain wall structure always not the greatest. So we look at an old Victorian home that's weatherboard clad, hard to start plaster. Simply whacking a glass wool bat in there might not be the best answer.
No, so each material has different hydroscopic properties, like ability to absorb moisture, both liquid and vapor. And so that's a bad characteristic of any insulation. You don't want it to absorb, like general. You don't want it to absorb moisture.
You want it to be hydrophobic.
Yeah, that's right. Yeah, you want to get rid of that moisture.
So hydrophobic or stop it from getting wet.
Well, yeah, but you've got to always assume worst case. Somehow I'm about to guess that this is going to get a plumbing leak, something's going to happen. Can it dry?
Yeah.
And so most of our insulation products, our standard glass wool, are treated with chemicals to try and reduce the ability for them to absorb that moisture. But as we know with the glass wool bat, if you leave it outside in the rain, it mats up together and it's cactus. You got to chuck it.
I like that we've gone back to types of render, and I'm not sure if you know the answer to this, and I'm probably then just going to be relying on what your opinion on this depends. So I built a Hemp house, right? And I know Brad's built a Hemp house as well. My particular example had render on the outside and render on the inside, right? And in my mind, that was for the air tightness and wear resistive. Now, the hemp walls that we're building are 300 wide. Now, how that assembly is working from an R value point of view is the same theory as a glass wall. It's trapping air in there. Now, if we're not rendering the inside, because I know it is different if you're not rendering the outside, if we're not rendering the inside, which is the warm side of the assembly, are you still going to get wind washing on the inside? Is it going to impact the RVO of that wall if we haven't rendered the inside?
Only very marginal, yeah.
Okay.
Because the influence of wind washing is affected by density. If I have let's go back to glass wall as our analogy. If you get your standard ceiling bat, if you know it's a very light and fluffy thing, you pick up about middle of tags, it's clearly far more air than glass.
Yes.
If you blow air past that, it quite easily scours and gets very deep into the loft and therefore reduces the thermal performance. If I go to a higher density wall bat, or I go to start jumping to other fibrous products like the windwall walls, your Rockwool type products, which are, about 80 kilogram per cubic meter density as opposed to your high 20s at most for glass wool. And you've got a far denser product, far smaller air gaps. And so it's much more difficult for the air to move into that space.
So then that is the same with mineral wool or rock wool when you're using that as an outside of that weather resistive barrier where, and I think it's a conversation I had with you, isn't this being impacted by wind washing because our ventilator cavity is then immediately on the outside of that exposed rock wool. But I think then your comment was because it's so dense, it's negligible.
And there's a study somewhere that they did a study on this, and I think once it hits a certain density, I think it had 96 kilograms a cubic meter, it actually the wind washing practically just goes.
Diminishes. And it's the same for wood fibre as well?
Yeah. And so again, the first metric you look at is density. So your standard wood fibre boards are in the order of maybe 60 kilogram per cubic meter density. So getting twice that of your best glass wool, getting towards your Rockwool type density.
If you've got a dense insulation like hemp or Rockwool or wood fibre, do we also see benefits of thermal mass in those particular products?
And thermal mass, can you explain how thermal mass isn't insulation either? They're two different things.
So yes, the denser the product is inherently, it's got more weight to it, and weight is related to the ability of a material absorb and retain heat. What is thermal mass? It's a material characteristic to store heat, but in order to store that heat, it needs to be able to absorb that heat. And so a material with very high thermal mass is classic example, something like concrete. Very high thermal mass, yes, but also very poor insulator because the inherent ability of that material to absorb heat also means it's very good at conducting that heat. And so if I use, say, a precast concrete wall and put it on the interior of my building, then it's got very good thermal mass, but very poor RDA, very poor thermal resistance because it absorbs that heat, allows that heat to carry through the depth of that precast wall and then just disappears towards the exterior.
So now for my house, for example, at the moment, I have a standard slab poured. I'm now about to put 75 mil XPS insulation on top, and then I'm going to pull 100 mil of infill concrete. Is that now getting the best of both worlds where I've got a great thermal mass like a battery for the home, but also that complete continuous layer is stopping that resistance that heat being able to travel through?
Yeah, that's basically right, exactly. So your screed, your finish slab on top of the XPS is providing really good thermal mass. It's not conducting through to the exterior, to the ground, because you put the XPS in between. No. And your battery analogy is perfect because you think about it out of the electricity grid, batteries do not create electricity. Things that create bulk electricity are your fossil fuel power plants, your wind, your solar plants.
Yeah.
They're the ones that create the electrons. The battery's just stored in it. If you've got no means of generating those electrons in the first place, there's no point having a battery. In the same way as with thermal mass, it's just a store of heat. It's not a creator of heat.
does it matter as much in a passive house?
No, because the passive house has inherently got a high thermal inertia to it.
So let's talk about passive house. Certified passive house, modelled, blower door, hitting all the metrics, certified, plap on the wall. Does that house perform differently if the clients are living in there, showering, eating, and there's no furniture? They're just sleeping on the ground. Does that house perform like noticeably different than if there was furniture in the house?
So it will almost certainly tend to fluctuate a bit more than the house with lots of thermal mass, be that furniture or something.
Yeah. Okay. And is any of that taken into consideration when you're modelling?
So there's some standard factors that are applied. But again, it's far less important than in a co-built house, because the way in which you dot that envelope is creating the thermal inertia itself, that trapped air mass within the house. You know, we're assuming there's cabinetry in there and there's an oven and a whole bunch of other stuff. You know, there's tons and tons of stuff in our houses, all of which inherently have thermal mass too.
So I want to go back to insulation, where we talk about roofs, and let's just assume a truss roof for a minute. Should we be insulating at the bottom chord or hit it at the top chord, like the warm roof versus cold roof? Because then the second question today, is a warm roof insulating at the top chord, or is a warm roof insulating externally? I don't know about you, but we're designing with rafters constantly at the moment, because there is that clause now in the NCC that pretty much means you have to insulate at the top chord.
It's also tricky too, because if you start talking about cold roofs, you got to, like the NCC stating, you got to ventilate that. And then if we're talking about airtight buildings, I mean, it technically is above your, or in most cases above your intelligent membrane. But if you don't have an intelligent membrane and you have a cold roof and you're relying on your external membrane to create airtightness, then you're potentially creating an issue up there.
But let's see to go back a sec. Like imagine, like you have to now have your external rack not airtight.
And so the construction code is essentially it's requiring you ensure that external membrane is not airtight. You've got to have that opening there. If you've got the potential for wind washing across those lighter fluffy bats, as you're letting that air come into the even drawer across the top of the bats. And so what you're seeing a lot of details, not so much in Australia, but internationally, is they'll put a bifold, and that first metre or two in from the eave, just a bit of ply or something.
That's assuming you have an eave though.
Or, well, at least from wherever that gap is on top of the wall, over that first metre or two of the bats, just where that air's coming in to reduce that scour and air washing effect on the bat as that air moves through that void and up out through.
Just like sitting here, like thinking there's so many fucking things you need to think about when you're building a house that could create risk. Like, and you know, this is where I kind of go back to and Sven talked about this a lot. Your real insurance policy is a certified passive house. That's your insurance policy right there.
Yeah, absolutely. The quality checking process with passive house is what you're buying.
Yeah, correct. Now, now, you know, potential clients listen to this about me and Matt. Like I would say, are good builders, and we think about all of these things. So I guess the risk when people are employing us is lower, but I'm thinking about people who are listening to this podcast and their brain's just exploding now, just thinking, fuck, how am I managing all this risk? A really easy solution is just to get a certified building.
Yes, but I think the key phrase there is managing risk. It's not zero risk.
Yes.
All we can do in life is manage and mitigate the risk as best we possibly can.
Yeah. If you're a young kid starting out, or a young builder, or a young architect, I think it's really important that you do your first 2-3 houses as a certified. So you know what to expect.
Yeah, exactly. So you know what the process is, so it becomes part of
just process. And this is the issue I now have, and this is probably a whole other conversation, is the apprentices that we're now producing only know one way of doing, and it's awesome doing. So what happens when they want to go out by themselves and they have to pick up the other 99% of the work that's out there that's pure crap? Now what do? Because they're not designed and haven't been taught to build to a low standard. And how do they pick up that first job? Because they're going to be way more expensive.
Yeah, well, I mean, let's hope by the time that happens that the actual the level of quality and the standard increases, and they have to. And then there's education from clients coming through. You know, I feel like, you know, every day that goes past now, there's more and more people demanding this stuff. Like,
I'd have everyone demands it, but can they afford it? And there's an
I mean,
it's setting up on top.
yeah, but that's okay. So if their number one goal is to have a healthy building, let's forget about energy efficiency, all that kind of stuff. If their number one goal is to have a healthy building, then everything else falls underneath that. So the joinery, the finishes, the fixtures, all of that becomes secondary to performance. If that swings around and aesthetics and everything like that is for a top priority, well, I know that building's not for me. It's I'll just walk away from it. And I'm starting to see more and more people, well, 100% of people come to me wanting performance.
I just want to go back to we just talked about particularly about testing and rounding off insulation. Testing insulation is very important. And it's not as simple as just picking up the thermal camera and walking around and checking, because that doesn't tell you the answers. It needs to be a difference from temperature inside to outside to actually check it.
And remember, and this comes back to our discussion about conduction, convection, and radiation. What's the thermal camera measuring? It's measuring radiation. And what did we say about radiation? It's a material property. So different materials emit at different ways. So a material, I could have a black material and a white material at the same temperature, but they will be emitting differently, and therefore they will appear to be a different temperature on your thermal imager.
Yeah, so really the best way to do a thermal imaging, like how we test our insulation, is we'll do a visual walkthrough and kind of have a team on site visually watching why they get installed. I don't know, the people that we use actually care about and stuff, so they are documenting too. They'll document the corner and how they'd installed it, so there is that reference point. And then we'll try as best as we can to either heat or cool the house inside and go around with a camera and check it. And sometimes it's really, really hard. Sometimes we physically can't do it. In winter coming up, it's a bit easier. But in summer, when it's a hot day, it can be quite difficult.
And that's a perfectly valid use of a thermal imager, assuming, as I think you mean, you've got your stud fray, you've got your glass wall in there, or polyester, whatever the insulation it is, bioplastable and membranes going on. So as long as you would be looking in that frame only at the wall and not the wall and the window together, because the window will give you spurious results, because its emissivity is vastly different to that of the glass wall and the timber.
So you kind of have to be up close, really.
You just focus your effort on, it's that image you're looking at is relative to what's in the field of view of the sensor.
Yeah.
And you're just looking within that space and going, right, here's my wall cavity. There's 4 bays here. There's a little purpley dark coloured spot right there in that corner. I'm not sure if I've got that bat right in there. Let's pull it out.
Yeah. And how much can you compress those bats? Because what percentage can we, because sometimes we've used when we do the internal cavity bat, we actually use a 50 mil polyester, which they're quite dense, but our battens are only 45. We also usually put a final packer, so we're not compressing it, but you can compress them slightly.
Yeah, you can to an extent. And again, it depends on the density of the bat to start with. So the lightweight, fluffy glass wall bats can compress a modest amount, and it's called 10 to 20% maybe. What really matters with insulation is its continuity. So exactly what you're talking about with your thermal imager and being diligent in installing it. Make sure you've got it perfectly installed in those cavities. A bit of modest compression I wouldn't be too fussed about. It's that continuity there.
Yeah, and that means around your windows, spray foam here, with a closed self spray foam, or wedging in some glass, or we really need to. You've got to make sure that it is. In Melbourne, because I know it depends where you are, we want that 360 layer around that whole house.
This is a nice segue to probably a question I've got. Now, whenever we've done slabs, I've always got offcuts at XPS, right? And it just kills me that just gets thrown away, right? There's not a huge amount. There's no recycling facilities at the moment. I know that there is some chatter at the moment that's starting to change. Now, we keep all of ours, and then we use it for our external wall junctions. Now, someone has actually asked me before, are you worried about any risk there? Because I just think in my mind, well, that can get wet. It's not going to get covered up immediately, and we just put it in as we're framing so it doesn't get forgotten about. Is there a risk in our climate, which is reasonably mild, of using XPS blocks in that wall junction.
So in a heating-dominated climate, remember what you want fundamentally is you want increasing vapor permeance
Yes.
as you move out through your assembly.
Yes.
And so a foam like an XPS is relatively vapor impermeable,
Yes.
whereas something like glass wool is very vapor permeable.
Yeah.
So your ideal assembly is, this is an imaginary assembly course, but if you've got an under frame, we whack XPS on the interior face and put glass wool on the outside.
Yep.
That's better in your heating dominated climate than the inverse of putting the XPS on the outside.
Yep.
But in the summer, it's reversed. So no one should go away and actually build what I've just described. Either of those two options, because they're both scary written all over them. Because in the summer, if you build that first option, especially on the inside of the stud in Melbourne, then the vapor drive is towards the interior. When you air condition your house, depending on what set point temperature you have it at, and depending on the thickness of the XPS versus the glass wool, you might be below the dew point.
What we're talking about, Howard, is great because it's getting people thinking. It's getting there. Because there's not one solution for every different scenario. Yeah, okay. So in your professional opinion, should we stop using those XPS offcuts in that scenario?
Well, you're also putting an internal air and vapor control product in, and you for HRV.
Yes.
And so on that basis, and as you said, you build in a relatively mild climate, Melbourne, then the risks are reduced doing that. Now, if you told me I had so much XPS in this job, so I've just whacked it along the outside of my 140 frame on a whole facade, then I've got a problem with that.
Yeah.
But intuitively, it feels like in isolated spots like those wall junctions where you've got a tricky little corner, okay.
And there's obviously a couple of reasons why I like to do it. One, that it doesn't get wet, but also it's stopping that XPS going into landfill and it's getting a reimagined life.
Yeah.
I wonder if we leave it there, Cam. Like, I think I'm going to really enjoy just think back to this and probably have to listen to it for a few times because there's so much to unpack there. But also, I love this episode because I think it's going to get a lot of people just thinking. It's going to make people stop and think because as we demonstrated, not all insulation is equal. They're all different. They're all for different purposes, perform differently under different conditions. And I think the biggest takeaway is modelling, woofy analysis, managing moisture. Oh, what else is there to add to that? It's the word depending. There's a lot of depending. There's a lot of depending. Yeah. And there's not one kind of like vinegar stroke, which just is, well, this is how we should build. Like, it depends.
Yeah, I think we've got to set aside the black and white. They will work, they will fail.
Yeah.
Because we can't say that definitively on any one project, any one location. It's a game of probabilities, and we're simply trying to reduce the probability of bad they're taking.